Hello, my name is Nathan, and I'm going to talk about the challenges of radiopharmaceutical treatments. Our learning objectives for this will be to differentiate alpha and beta radiopharmaceuticals, understand how radiopharmaceuticals are introduced into the patient, evaluate negative impacts of using radiopharmaceuticals, understand the effectiveness of using radiopharmaceuticals, and to recognize treatment plans using radiopharmaceuticals. What is a radiopharmaceutical? It's a unique pharmaceutical that has radionuclide as a radioactive isotope, and it's connected to a targeting agent. And the targeting agent is actually attracted to a particular organ or a tissue. It's used in nuclear medicine primarily for diagnostic imaging and for therapeutic use. Radiopharmaceutical has three parts. They have the radioactive isotope, which is a irradiated molecule. Examples of this is luteum-177, radium-223, uridium-90, and iodine-133. They're essentially made with nuclear fusion, neutron reactions, and a cyclotron. Neutron reactions is made from a nuclear reactor, and the cyclotron is made by a machine that spins very, very fast and adds a lot of neutrons into it. Essentially, they're all made by adding neutrons to the molecule, the beginning molecule. They're targeting molecules also that are used to bind to specific receptors on the targeted cells. These consist of nanoparticles, antibodies, iodides, and peptides. And then when they want to put the irradiated molecule with the targeting molecule, they put it back into the cyclotron. The cyclotron spins very, very fast, and it mixes it up like a blender kind of together, and then we have our radiopharmaceutical. Alpha and beta particles. Alpha versus beta. So we have our particles. You look at the right side of this slide. Alpha particles are a lot larger, they have more energy, and they have a longer LET, linear energy transfer. They are both carcinogenic, alpha and beta particles. The difference between the cell kill is the alpha particle has more energy, therefore can make a double strand break on DNA, and it's more probable that a beta will only do a single, which means that the cell with a beta can regenerate and heal. How are they administered? Radiopharmaceuticals can be injected, infused, inhaled, ingested, and delivered topically. For therapeutical use, they're primarily injected into the patient. A treatment plan consists of a theranostic tumor board. It's led by authorized users such as the people in nuclear medicine, radiation oncology. It's got the surgeons, the medical oncology, urology, and endocrinology units. So it's got a multidisciplinary involvement that they all work as one team, and it's to select the patient, make safety protocols, any follow-ups like labs and imaging. They put in the plan, the outcomes, and the patient quality of life. So all this goes into it while they're selecting the patient to actually do the procedure too. Another thing that is not in this list is the coordination of the physicians, the physicists, pharmacists, nurses, radiation safety team, the medical representatives that have to be there when they use the radionuclides, the delivery, the schedule of radiopharmaceuticals, room prep, waste handling, room clearance that the radiation safety team has to conduct, dose tracking from the oncologists, follow-up labs, patient education, and whether or not they even have insurance. Could be because of the cost might be an issue. Now we're going to look at how effective are radiopharmaceuticals. So the effectiveness does depend on the location of the cancer. If the tumor is able to uptake the targeting material, the method of administration, how much they're able to distribute, how far the radiopharmaceutical has to go through tissue to travel, uh, the actual size of the radiopharmaceutical, like before we were talking about alpha and beta particles, um, the half life. Because of shipping transportation, you may have to go to a different state to actually get that radiopharmaceutical treatment, because of the half life. That just can't travel that far from where it's manufactured. And like I just said, it's where it's manufactured and how fast they can deliver it. On the left, it shows a kind of like a little breakdown of different kind of cancers and how effective they are. All of these are injected into the patient, and typically they're injected right at the site of the cancer. So the most beneficial radiopharmaceutical treatments are for thyroid cancer, non-Hodgkin's lymphoma, and they've actually come out with they're working on a couple of new radiopharmaceuticals for lymphoma also. Another one is prostate cancer and liver cancer in the liver. Um, these all have a very high probability of um, being able to cure the cancer or make it in remission and give the patient a little bit longer quality of life. So, what are some of the positives and negatives? Some of the positives include they're highly specified for target uptake. They can control symptoms, shrink tumors, and systemic metastatic cancer. Gamma emission and beta particles lead to a good visualization of target distribution. Lower systemic malignancy than external beam radiation. Can be used in conjunction with or after other treatment options. Safer delivery systems. Higher effectiveness than alternatives. Some of the negatives are they're highly toxic. Once they get injected into the body, they're toxic to kidneys, the renal, salivary glands, and our bone marrow production. Um, they have very short half-lives, limited availability, and imaging limitations when it comes to alpha particles. Um, Dosimetry and personalized treatment plans do have their limitations. They have a bad perception and few options for cardiovascular, inflammatory, and neurodegenerative diseases. And sometimes they do go off target and get reuptake in other areas of the body. So some of the negatives that I found, there's less than 75 radiopharmaceutical companies in the United States. So that's very limiting as far as transportation and availability of the drugs. And there's about 200 or less cyclotrons that actually produce the radiopharmaceuticals. Indiana, however, is the biggest radiopharmaceutical distributor in the world. Other honorable mentions are New York, Texas, California, Wisconsin, Missouri, and Massachusetts. One of the biggest problems as far as transportation and distributing is how heavily regulated the transportation of a radioactive isotope across state lines or even within the state is. So a courier has to have the proper permits and everything to pick up from a radiopharmaceutical pharmacy. They pick it up, they have to relabel everything, and they have to package it so that way if there's any accident or anything, there will not be a big spill. And then once they transport it, it has to be in a approved carrier mode of transportation. And once it arrives at a hospital, it has to go through the physicist will be there and the radiation safety officer, and it has to go to a hot lab. When it's in the hot lab, it has to be surveyed for any leaks and unpackaged, and then they have to make sure that the radioactive pharmaceutical is the grade that they need for the procedure. So, in conclusion, we reviewed the effectiveness of using radiopharmaceuticals, identified how radiopharmaceuticals are introduced into the patient, evaluated the negatives of using radiopharmaceuticals, reviewed treatment plans using radiopharmaceuticals, distinguished the difference between alpha and beta radiopharmaceuticals. Here are my references, and thank you for watching.